Today's video is going to start out with a quizkin that will review some of the things that we learned about electrolysis, particularly metal plating, and then we're going to move on to discover galvanic or voltaic cells. Voltaic cells are commonly called batteries, and they use a spontaneous reaction to produce an electrical current, kind of the opposite of electrolysis. This quizkin tells us that a jeweler is plating silver onto 1-inch steel cubes. So this is 1 inch on a side. So your cube would look like this. And the cathode reaction is given here. Silver 1 plus reduces to silver by gaining 1 electron. And then the question is how long, so we're looking for a time here, will she have to leave the cubes in a solution? So the solution, of course, would have to have silver ions in it at 3 amps, so there's our current, for a 4,000 angstrom thick coating. An angstrom is 10 to the minus 10th meters. And the density of silver is also given as 10.5 grams per milliliter. So we have a bunch of data there. Stop the video, see if you can figure out what to do here. I'll give you a hint. You'll have to figure out the mass that's got to be plated onto this cube before you can do anything else. Then I'll bring you an answer and a solution after a bit. I'm imagining my cube here. I'm going to just reproduce a simple sketch of a cube. And a cube has got 6 sides. And each side here, it says, is 1 inch by 1 inch. But I think I want to work in centimeters, because if I can get my volume in cubic centimeters, I can find mass because the density is in grams per cubic centimeter. So that's 1 inch or 2.54 centimeters by 2.54 centimeters for each side. And then 6 times because there are 6 sides in the cube. That will tell me the total area that I have to coat with silver. And if I take the area times the thickness, then I should have the volume. So my strategy here is going to be I'll find volume by taking 2.54 centimeters and squaring it, and then multiplying by 6, and then I'll multiply by the thickness, but I want the thickness to get in the appropriate units. So let's work on that. The thickness is supposed to be 4,000 angstroms. And I said earlier that an angstrom is 10 to the negative 10th meters. But I don't want meters either, I want centimeters, so that I can put that together with this unit and get cubic centimeters. So 1 meter is 100 centimeters, and that will give me a thickness in centimeters. And that's 4.000 times 10 to the negative 5th in centimeters. So my volume of silver is going to be equal to 2.54 centimeters squared times 6 sides times 4.000 times 10 to the negative 5th centimeters. And this will come out to cubic centimeters, which is the same thing as milliliters. The answer here is 0.00155 cubic centimeters. So that means the mass of silver that I'll have to plate onto these cubes is equal to density times volume, which is 10.5 grams per milliliter times the volume of 0.00155 milliliters. When I do my arithmetic, I get 0.0163 grams of silver. Now we can do some electrochemistry. Starting with that quantity, 0.0163 grams of silver, the first thing I want to do is convert that to moles. Molar mass of silver is 107.9 grams per mole. So now I have moles of silver. But from the half reaction that I had, Ag plus 1 electron makes Ag, I know that 1 mole of Ag requires 1 mole of electrons. So now I have moles of electrons. Faraday's constant tells me that that mole of electrons has a charge of 96,500 coulombs. So now I have the charge that I'm going to need. And my current was 3 amps. But remember, an amp is a coulomb per second. So I can divide by that current, 3 coulombs per second, to get rid of my coulombs, and that gives me my time unit that I'm looking for. When I do the arithmetic, I get 4.85 seconds as my answer. Well, now let's get into voltaic cells. A voltaic cell is just an electrochemical system that uses a spontaneous reaction to force current flow in an external circuit. Another name for voltaic cells is galvanic cells, but I don't think that's used quite as commonly these days. The key to making a voltaic cell work is that the reduction and the oxidation occur in separate spaces called half cells. I'm going to build a simple model here just using beakers and a strip of copper in one of the beakers, and that copper is oxidizing to produce Cu2+. In the other half cell, I have a reduction. I have a piece of silver that's in a silver 1 solution, but the silver 1 ions are reducing to silver in that half cell. So what's going on in the oxidation half cell here is that the copper is oxidizing to copper 2+, but it's also yielding electrons. And those electrons have to go somewhere. They have to leave the half cell. What's happening in the reduction is Ag1+ is reacting with an electron to produce the silver that's in this bar. And so that requires that an electron come from somewhere else. Connecting the half cells with a conductor, like a piece of wire or a circuit in a flashlight or an iPod or something like that, creates electron flow, and that's electrical current. So the electrons that are produced in the oxidation half cell, called the anode cell, flow down the wire, and they are exactly the electrons that are needed in the reduction half cell. Now, there's a slight problem that's going to develop. As I lose more and more negative charge, and I gain a bunch of copper 2+ ions, this side, this half cell, becomes very positively charged. And by the same token, as I lose a bunch of Ag pluses by reduction and gain a whole bunch of electrons, the other half cell is going to become very negative. Well, nature hates separating positive and negative charges from each other. They're very attracted to each other, and so a bunch of potential energy is going to build up, and of course then the whole system will stop. So we have to have a way to get the negatives to this side and the positives to this side so that we can complete the circuit. Now, what balances this charge imbalance and allows the circuit to be complete is something called a salt bridge. Now, I've got here in my model a potassium iodide salt bridge. It's made from a U-shaped tube, and in the two ends you have maybe glass wool or some cotton or something that will keep the solution in there but allow ions to flow freely into and out of the tube. So there would be a solution that has K+ ions and I- ions in there. Well, here's how this works. On the right-hand side, which is the oxidation half cell, because I'm oxidizing, I'm losing negatives and I'm gaining positives inside the half cell. So a positive charge gets built up over here. On the left-hand side, which is the cathode side, I'm losing pluses because silver ions are reducing, and I'm gaining electrons because electrons are coming into the cell. Somehow the salt bridge has to combat that differential of charge. Here's how it does it. To keep the anode half cell neutral, you have to combat the fact that you have more and more positive ions in there. The positive ions, the cations produced in this oxidation, will go into the salt bridge because they can leak into the salt bridge. But remember, this salt bridge contains I- ions because it's potassium iodide. So these I- can leak out of the salt bridge and join the solution. That makes negative charge increase and positive charge decrease and brings this half cell back into balance. What's going on the cathode side, remember, is that silver ions are being reduced. That silver had to have an anion in this solution originally, so it was something like maybe nitrate. Those negatively charged nitrates start to build up in here with no silver to balance them. So those nitrates can migrate into the salt bridge and leave that half cell. Remember, there are potassium ions in this Ki solution, and so those potassium ions are positive. They can migrate out of the salt bridge and bring the charge back into balance because it's becoming too negative on this side. So as electrons, negative charge, flow counterclockwise in this circuit, that motion continues because the negatively charged anion goes into the salt bridge and negatively charged I- goes out of the salt bridge back into the oxidation side. And the circuit runs counterclockwise around and around and around as long as that salt bridge is still there. We have a standardized way of describing voltaic cells without having to draw a big picture with beakers and things like that, and it's called cell notation or line notation. And here's how it works. You first write down the anode. What's the anode made of? Then you put a vertical line, and then you write the anode electrolyte. In other words, what is the solution that it's immersed in? Then you put a double line that represents the salt bridge, and then you put the cathode electrolyte. You list that, and then you put a single vertical line, and then you finish out by putting the cathode. So this is standard line notation. It's easy to remember how to make this because it goes A, B, C. A for anode, B for bridge, C for cathode. What would be the line notation for this voltaic cell that we were just looking at? Well, we know on the right-hand side that that's where the oxidation is occurring. So copper is our anode, and copper 2+ is our anode electrolyte. So we'd start out our line notation by writing Cu solid, that's our anode, vertical line, Cu2+ aqueous, because that's our electrolyte. Then bridge, and then we put our cathode electrolyte, which is a silver 1+ aqueous solution, so Ag plus aqueous, and then a vertical line separates the electrolyte from the electrode, and our electrode is a piece of silver, so we put Ags. To really understand voltaic cells, we have to talk about cell potential. The idea of potential, which is sometimes called electromotive force, and that's abbreviated EMF by electrical engineers, or voltage by electricians and people who work with electricity on a regular basis. It's really a measure of kind of the force behind electrons. What it does is it describes the amount of energy that can be delivered by a current. So if you have a 10 amp current, all 10 amp currents aren't created equal. A 10 amp current with a high voltage carries more energy than a 10 amp current with a low voltage. Here's an analogy. If you get hit by a bicycle that's moving 10 miles an hour, that will hurt a little bit. If you get hit by a car that's going 10 miles an hour, that will hurt a lot. It's sort of like a measure of how much force is behind the object that's moving at that speed. Only it's not speed here, it's electrical current. The SI unit of potential, or EMF, is called the volt. And 1 volt is equal to 1 joule of energy per coulomb of charge. So let's relate this to electrochemistry in a voltaic cell. Cell potential, which is abbreviated E cell, is the maximum potential, the maximum EMF or voltage that can be generated for a given voltaic cell. Here's what it depends on. The half cell's composition. What are the two half cells made of? Some combinations give higher voltage than others. An example would be a car battery. The way a car battery is put together, that voltaic cell gives you about 12 volts of potential. A AA battery that you would put in your calculator or a flashlight or something generates a potential of about 1.5 volts. The difference is what are the half cells made of. Another thing that is a factor is the concentrations of the electrolyte. So you start out with certain concentration, and then as the life of the battery goes on, the concentrations change. And as those concentrations change, the amount of voltage that the battery can produce also changes, and so batteries go dead. And then another factor is the temperature. If you drive a car in Wisconsin like I do, you know that in the wintertime, when it gets quite cold outside, it's hard to start your car sometimes because your battery doesn't produce very much electrical potential when it's cold out. Well, just so we can talk about this and make comparisons and then go on to make predictions, we have something that we call standard cell potential. And this is E cell with the little degree sign, like you've seen standards before for Gibbs free energy or enthalpy or entropy. And the conditions are just about the same. The potential for a voltaic cell is called the standard cell potential when the pressure is 1 atmosphere. We've seen that before. The temperature is 25 degrees C. But then here's a new stipulation. The concentration of all electrolytes are 1 mole per liter. Now we could measure cell potential, but if you wanted to design a voltaic cell and design a good one, it'd be nice to be able to make a prediction. So we can do that through something called reduction potentials. Each half cell in a cell has the potential to be the reduction half cell. In every voltaic cell, one half cell is going to be a spontaneous reduction, and the other one is going to be a spontaneous oxidation. You just don't know which one is which unless you test it or make a prediction. So the reduction potential, which is abbreviated E-red, is a measure, and you can measure this in volts, of the potential of that half cell to be a reduction half cell. The only way that you can compare one half cell to another, though, is to have a common reference point. And so we're going to talk about standard reduction potentials to provide us with that common reference point so we can compare half cells with each other and determine which one's better at being a reduction. And that turns out to have some good applications. If you compare two half cells, the one that has the highest reduction potential is the actual reduction. It's the actual cathode half cell. And then the other one would have to be the spontaneous oxidation. So here's how we do this. The standard reduction potential for comparison purposes. The measured half cell is at standard conditions. So that means the solution concentration is 1 molar. It means that the pressure is 1 atmosphere. And it means that the temperature is 25 degrees C. But the other stipulation is the other half cell is what we call the standard hydrogen half cell. So here's what the standard hydrogen half cell is. You have an electrolytic solution that's 1.00 molar H+. So it's an acid. And the electrode in this half cell is what we call the standard hydrogen electrode. Standard hydrogen electrode is a little bit complicated, but it is a very good reference point. So your standard hydrogen electrode looks kind of like this. This is a sort of a schematic of how this might look. Here's a glass tube, maybe, upside down. And running through the top of that tube, sealed into it, is a wire, probably a platinum wire. And here's a piece of platinum. You can choose platinum. It's a good choice because it's really inert. It doesn't react very readily. There's a little sidearm on this tube, and into that sidearm is pumped hydrogen gas. And that hydrogen gas is at 1 atmosphere, so that it's standard. Hydrogen gas comes down and sticks to this piece of platinum, and so we have little bubbles of hydrogen gas sticking to the platinum. But remember, this whole thing is immersed in a beaker that has an electrolytic solution that is 1.00 molar H+. The reduction half reaction that takes place here is, if this is a reduction, the H+, the two H+ from the aqueous solution, gain 2 electrons that come down the wire and produce H2 gas. Now, of course, this can run both ways depending on what's on the other half cell. This is why this is a standard. The scientists who set this up have established that the reduction potential, the potential for this half cell to be a reduction, is 0. It's not a measured value, it's a defined value. We're calling this 0. Everything else will be compared with this. Some things might be higher, some things might be lower, but this is the standard against which all half cells will be measured. So if you wanted to measure the reduction potential of, say, this copper-2 half cell, what you would do is you'd hook it up so that it was one of the half cells. The other half cell is the standard hydrogen half cell. Put a salt bridge in, hook up a wire, and then put a voltmeter in the circuit. This voltmeter will measure the cell potential. Now, if the cell potential turns out to be a negative number, then what that means is hydrogen is more easily reduced in the hydrogen half cell. So that means the measured half cell, this cell over here, would be an oxidation, and the cell over here would be the reduction half reaction. If that takes place, then the hydrogen half reaction would be H+ plus 2 electrons making H2. And since this is the reduction on this side, the direction of electron flow is this way in the circuit. Now on the other hand, if you get a positive number in here, then that means the measured cell is more likely to be reduced, and the hydrogen cell is more easily oxidized. So that means the reduction's over here, the oxidation's over here, and the reaction on the hydrogen half cell side is H2 oxidizing to 2 H pluses and giving up 2 electrons. And because the 2 electrons are coming out of here, our direction of electron flow is this way in the circuit. That's with a positive cell potential. Well, in fact, if you do put this copper-2 half cell in there, you will get a positive 0.34 volts. That's what it'll measure under standard conditions. What does that mean? Well, that means the reduction potential is positive 0.34 volts. So the reduction in this cell is happening in the copper half cell, and it means that Cu2 plus will be gaining 2 electrons and reducing to Cu. So this is the direction of that half reaction. Electrons are being gained in a reduction, and so the electrons are flowing this way in the circuit. That means the electrons over here have to be flowing out of the half cell, and this is the oxidation half cell over here. So that means H2 from the little bubbles on the platinum bar are oxidizing to make 2 H pluses, and they're giving up those 2 electrons that are going to go down the wire. Here's a different example. If you put a piece of iron in an iron 2 solution that's 1 molar, put a salt bridge in, hook it up to the standard hydrogen electrode, you'll get a negative 0.44 volts on your voltmeter. That's your reduction potential because that's the cell potential against the standard hydrogen electrode. Remember, this is defined, the reduction potential of the standard hydrogen electron is defined as 0. So if this is 0.44 in this circuit, that means the reduction potential for this half cell is negative 0.44 volts. So what does that mean? Well, it means that the hydrogen electrode is going to be the reduction. So we'll have in this half cell H plus gaining 2 electrons to make H2. So the electrons are flowing into this half cell. That means they're flowing out of this half cell, and the iron is going to actually oxidize to iron 2 plus. So our oxidation is Fe oxidizes to Fe2 plus by releasing those 2 electrons. So you take a whole bunch of different half cells and hook them all up to the standard hydrogen electrode in the standard hydrogen half cell, and you read what the voltmeter says, and then you make a table. And this has been done for many, many half cells, and you can look up in reference tables on the web or in reference books and find out what are the standard reduction potentials for a lot of half cells. So what do you do with it? Well, you have 2 main uses for reduction potentials. One of them is predicting the potential of a voltaic cell and predicting what the cell reaction will be. How do you do it? The first thing you do is determine the 2 possible reductions that might take place. And then the second thing you have to do is look up the reduction potential for each one of those 2. The most positive value of reduction potential, well, that's going to be the actual reduction half cell. The other half cell is an oxidation. And so you would take the reduction that you've proposed for that half cell, flip it around, and the oxidation potential for that half cell is just the opposite of the reduction potential that you looked up. Then you can find the cell potential by summing up the reduction potential and the oxidation potential, and you'll get the cell potential in volts. Now this is standard cell potential under standard conditions. In the next video we're going to find out what do you do if you're not under standard conditions, but for now we're just going to stick with the standard. So for example, what is the cell reaction and the standard cell potential for a copper-2 half cell put together with an iron 2 half cell? Well, first of all, let's kind of draw a picture of this thing. Here I have one container, and in this container I have an iron 2 solution. There's a salt bridge that connects that container to a second container. And in here I have copper 2 ions, which would look blue in color. And my electrode is a bar of copper. In the other cell, I have a bar of iron, and the two are connected by a wire that has a voltmeter here, and it's our job to predict what's it going to say in that voltmeter and which direction are the electrons going to flow. Well, here are the two potential reductions that could happen. If the half cell on the left is a reduction half cell, here's what would happen. Fe2 plus would get 2 electrons coming down the wire and reduce to iron. On the other hand, if the right-hand cell is the reduction cell, then copper 2 would get the 2 electrons and reduce to copper. So let's look up the reduction potentials for both of them. Well, we don't have to because we just did these in our two examples. We saw that the standard reduction potential for iron 2 was negative 0.44 volts. We also saw that the standard reduction potential for copper 2 was positive 0.34 volts. Now, if you didn't happen to remember that, you can look them up because they're in reference tables everywhere. Well, here's the decision. We look at the two reduction potentials and we look for the one that is most positive. Well, E red is negative for the iron reduction, and it's a positive 0.34, so that's the one that's most positive. Here's what that means. The actual reduction here is going to be copper 2 plus 2 electrons to make copper. And E red, the standard reduction potential, is positive 0.34 volts. That means the other half reaction is not a reduction but an oxidation. So I'll reverse it. Fe oxidizes to Fe2 plus and gives up 2 electrons. Now this isn't going to have a reduction potential, it's going to have an oxidation potential, and it is the negative of the reduction potential. Well, it was minus 0.44, so the oxidation potential is positive 0.44 volts. So what's the cell potential? We sum these up to find out what the standard cell potential is for this cell. And it's 0.34 plus 0.44, that's a positive 0.78 volts will be generated by this cell. What's the cell reaction? Copper 2 plus iron makes iron 2 plus copper. The direction of electron flow is going to be from the anode over here to the cathode over here. Well, another use for standard reduction potentials is predicting the spontaneity of a reaction. To do this, you first of all take a look at your situation, your physical situation, and determine what could be the possible reduction that might happen here and what could be the possible oxidation that might happen here, just based on what you have there. Then look up the reduction potential for the reduction, look up the oxidation potential for the oxidation, sum them together to find the cell potential. If the cell potential is positive, then you have a spontaneous reaction. If it's negative, well, you don't. So let's look at this example. If a strip of iron is put in a 1 molar copper solution at 25 degrees C, will a reaction occur or not? So here's a picture of that scenario. I have a solution of copper ions, Cu2 pluses, and I have a piece of iron inside there. The question is, will this copper reduce and will this iron oxidize? Because the iron can't reduce to a negative ion, and the copper can reduce, and so this is our potential reduction. If there's a spontaneous reaction, it's going to be this. Cu2 pluses are going to reduce to Cu, and Fe's are going to oxidize to Fe, we're going to say 2 plus, and give up 2 electrons. So does it happen? Well, the standard reduction potential for our proposed reduction here is a positive 0.34 volts. The standard reduction potential for iron we saw was negative 0.44 volts, so when you turn that into an oxidation potential, that's positive 0.44 volts. So when you sum these together and get E naught cell, you find out that it is positive 0.78 volts. Since this is positive E cell, then that means this reaction is spontaneous. So if you put a piece of iron in copper, you're going to get a reaction. Copper will reduce, iron will oxidize. Now let's change this around just to take a look at one that isn't spontaneous. Let's say you put a strip of copper in a 1 molar iron 2 solution would a reaction occur? So here's the physical setting. I have a solution that has Fe2 plus ions in it, and inside there is a piece of copper. The only thing that can oxidize here is the copper, so that would be Cu oxidizing to, we're going to say 2 plus, and giving up 2 electrons. The oxidation potential is the opposite of the reduction potential for the reverse reaction. So that's going to be negative 0.34 volts. The only reduction that can happen is iron would have to reduce to Fe from Fe2 plus. So that would be Fe2 plus 2 electrons making Fe. The reduction potential for that would be negative 0.44 volts, because that's what we saw when we did that example. If you sum up the ox and reduction to get E cell now, what you'll find out is you have a negative 0.78 volts. And since E cell is negative, this reaction would be non-spontaneous. Well, we've always been working with standards today, and of course it isn't always 25 degrees C, and you don't always have 1 molar concentrations, and so we need a way to deal with that, and you'll see that in the next video.